All right, guys, let's get started. Again, hit it up for DJ Drop Tables. How was your weekend?
It's pretty good. My friend Diamond C got sent to the hospital for huffing whippets.
He was huffing whippets.
Yeah, it's like, I don't do that stuff, but he huffed too many whippets over the weekend. So I had to take him to the hospital.
Don't do that.
Yeah.
That's okay. All right. So other announcements other than huffing whippets is that homework 1 is due on Monday at midnight. You should be able to submit on Gradescope. A bunch of you have already completed it. Who has not started? Wednesday. What did I say? Monday? Yeah, today's Monday. Wednesday. Whenever the 11th is. Right? Who has not started? Start. Just to make sure, okay? And the other thing, we will be releasing project number 1 on Wednesday as well. Again, the lecture on Wednesday will be all about what you're supposed to implement in project 1. And then so at the end, we'll talk about the sort of logistics of how you're going to go about and do this in the source code. And then, again, that'll be submitting on Gradescope as well. Okay? All right, so the other things that might be interesting to you are we have some upcoming database talks that are sort of somewhat relevant to what we're talking about in the course. This Friday over in the CIC building, we will have a talk from people from Salesforce. This is public. Salesforce is building a brand new database management system, distributed database system based on Postgres. And a lot of my former students, people who have taken this class, are now working on it in San Francisco in their brand new buildings, which are amazing. Then next week at the database group meeting on Monday, we'll have Ankur Goya, who is CMU alum. He was the former VP of engineering at MemSQL, which is an in-memory database that we can talk about later in the semester. So he has a new startup doing video analytic database stuff. And he'll be talking on Monday next week. And then the following Monday, so 2 weeks from now, we'll have somebody from Vertica come give a talk. So Vertica is a column store database system, one of the more famous ones, that was invented by my grad school advisors and got sold by HP, and they got sold off to a holding company a few years ago. But believe it or not, they actually have an office in Pittsburgh, and so he's going to come give a talk about what the kind of stuff they're doing here, and what are the newer things Vertica is doing. So if I say the word column store, it won't make sense right now. It should make sense by the end of this lecture, okay? Because we'll describe what that is. And I actually tried to get it up and running to give a demo, and too many installation errors, so I gave up. Okay. So again, these are all free to the public. There's pizza at this one, and this is just like fruit. So you can plan your meals accordingly. All right. So last class, we started talking about how we would want to design a disk-oriented database system. And again, I said a disk-oriented system is one where the database system assumes that the primary storage location of the database is on disk. And so we spent time talking about how we're actually going to organize the database at different levels, within files, within pages, and then within those pages, within tuples. And so the reason why we want to do all this is because we want to be able to support databases that are larger than the amount of memory that's available to us on a single machine. And yes, I know you can go distributed, you can go across multiple nodes. For now, we can ignore all that. Just saying you have a single box, how do we bring data in when we can't fit it all in DRAM? And so we finished up talking about slotted pages. This is just a quick refresher. So a slotted page was how we're going to organize tuples inside of a page so that we can move things around and we start packing in as many tuples as possible. So we have the slot array at the top, the fixed and variable length tuple data at the bottom, and we just keep adding things from the end to the beginning and from beginning to the end until we reach the middle and we don't have any more space. And so I said this is the primary way most database management systems out there that are Rowstore systems, which again I'll explain what that is in a second. This is primarily the way most database systems actually do this. But it's not the only way, and we ran out of time and we didn't discuss the other way, and so I'm going to briefly talk about that. So just again, this is put it in context. Most of what we'll talk about this semester will be this organization. The database system you'll be working on for your projects will use this type of organization. But again, it's not the only way. Another way to do is called log structured file organization. So the way this works is that instead of storing the full tuple inside our pages, we're instead just going to store the information about how that tuple was created or modified, right? So what do I mean by that? So let's say in our page, we're just going to start appending these log records And don't think of it like log records like a text file that are read by humans. Think of it as a log record that's some binary representation of what the change was. So we're going to record like I inserted this tuple, I updated this tuple, I deleted this tuple, right? And all we have to do is just keep appending every time we fill up the page, we just go create a new one and start appending more log records to that. And anybody think, I guess, why you'd want to do something like this? Yes?
It's easy to roll back.
It's easy to what?
Easy to roll back.
It's easy to roll back. Potentially, yes. Yeah, it's like if I have 1,000 columns and I update one, if I need to roll back, I just blow away the single update record. Yeah, that's one. Yes. She says fast writes. Absolutely, yes. So remember we said that especially in spinning disk hard drives, but even modern SSDs, it's much faster to do sequential writes and sequential reads or sequential access than random access. So if I'm back in this mode, and let's say I update 10 tuples, but they're all on different pages, now I have to go write and update the tuple across 10 different pages. But if I'm doing the log structure organization, then I just put my 10 writes into my single page, and I can write that out in one go. So so this idea is not new. Like it came out in the late 1980s, early 1990s, log structure file systems or log structure merge trees. But it's really probably in the last 10 years that this has taken off. And in part, this is because things like HDFS or S3, right? There's all these distributed file systems where they're append only. You can't do random updates. You can only keep appending records. So this style of storing your tuples it works great for that. So what's one obvious downside with this? She says read data. Absolutely, yes. So if I have to read a tuple now, I got to go back in time and look at the logs and try to figure out what does the tuple look like? Wait, what was the final result of the tuple? Right? So if say I'm updating some tuple here and I have 1,000 columns, but I don't update one of them, I got to go back and try to find where it inserted or updated the other 1,000 columns to put it back into the form that you want. Right? So there's ways to sort of speed that up. Right? You could build indexes and say, oh, if I'm looking for a particular tuple, here's how to jump to the particular offset in the log that has the data that I want. Or another thing you could do is say, just go and actually replay the log and compact it down into just one record per tuple, right? So I can take all these guys and then just convert it back into just almost their tuple form. So as I said, this is more common in more recent systems. Some of these you probably have heard about, HBase, Cassandra. There's a bunch of these distributed systems that are out there that are written in Go, things like CockroachDB, where they're all using RocksDB as the underlying storage manager, right? So the distributed execution layer is all in Go, but then underneath the covers, RocksDB is in C++. And so rather than writing their own storage manager, they just rely on this like as an embedded system. So RocksDB came from Facebook. Actually, RocksDB is originally based on LevelDB. LevelDB was written by Google. Then Facebook took it. First thing they did was remove mmap, right? And then they re-released it as RocksDB. So LevelDB is still out there, but pretty much everyone uses RocksDB. So again, so we're not really going to cover this the rest of the semester. It'll show up when we talk about distributed databases later on at the end. But for our purposes, we'll just assume that we're dealing with entirely slotted page systems. OK? All right. So for today's class, we want to now go a little bit deeper and talk about how we're actually going to represent the data in tuples. So again, we said the database is represented by a bunch of pages. So then we discussed how to break up the heap file into pages. And then with each page, we talked about how to represent the slotted array. And then we said roughly inside each slotted array, you have these slots. Then you have your tuples, have a header. And now inside the tuples, we want to say, what does the data actually look like for individual attributes or columns? How are we actually going to represent that? Then we'll go on and talk about how we actually store the metadata about what our tables look like. And then we'll talk about the storage model, the row store versus column store stuff. OK. So at a high level, a tuple is just a sequence of bytes. It's just a byte array, right? And it's up to the database management system to be able to interpret that byte array and make sense of it and say, oh yeah, this is an integer, this is a float, this is a string attribute. So that's essentially all what we're doing here. We're just organizing our tuples as these byte arrays. And then when it comes time to execute a query, we need to interpret what's actually in those byte arrays to produce the answer that we're looking for. And so this is what the catalog stuff we'll talk about in a second. This is how they're going to figure out, oh, I have 10 columns. First one's a 32-bit integer. The next one's a 64-bit float. Like, it uses that information to decide how to interpret and decipher those bytes. So the way we're going to use, for most database systems, the way we're going to represent data is for fixed length things like integers and floats is usually the same way that we would represent this in like C or C++. This is usually defined by what's called the IEEE 754 standard. Who here has heard of that before, the 754 standard? All right, a little bit less than last year. So the 754 standard is basically, for the industry, it's the specification of how to represent numbers in CPUs, like integers and floats and things like that. How many bits, is it big endian, little endian, have the twos complement in the front. All that is represented in that standard. So for fixed length types, again, integers, big ints, small ints, tiny ints, and then float and reals, we'll just follow the 754 standard. We'll discuss in a second about the fixed point decimals, but basically these are floating point and then these are fixed point, and this is something we in the database system will have to implement. For variable length things, varchars, var binary, text, and blobs, typically there's a header that says, here's the length of the blob I'm storing or the variable length field I'm storing. Maybe a checksum if it's a really big value, and then you have the sequence of bytes. So this is different than representing strings in C's where you have the null terminator character. We're instead going to have a prefix that tells us how big it is actually going to be. For dates and timestamps, this varies widely across different database systems. Right? There's no one way to actually do this. Most of the systems usually just store the number of seconds or microseconds or milliseconds since the Unix epoch, which is like January 1st, 1970. For Windows, I don't know what they do. And so in a bunch of systems too, also, you can say, oh, I want the date without the time, or I want the time without the date. Underneath the covers, it's still going to store the full timestamp. It's just the API that you use to access that data knows to strip out whatever part you don't need. Right? So some systems will actually just pack in just the date and store that as a smaller value. A bunch of systems actually don't do anything. So again, this is something we have to implement in our database system. This is something we implement in our database system. But for the fixed point values, we'll just rely on whatever C++ gives us, which is the underlying hardware. All right. So the thing we're going to go talk about now that's more interesting is, again, how do we actually compare these two, the fixed point versus floating point decimals? So if you want to have floating point decimals or variable precision numbers, right, these are inexact numbers that the CPU gives us, or C++ gives us. Like if I have a C program and I declare a variable, float, whatever, and give it a variable name, that's what we're getting when we declare a real or double or float in our database system as like the SQL type. Again, this is specified how you actually represent this, like the decimal point and the scope and the precision, all that's defined by the 754 standard. So these are going to be much faster to execute or to operate on than the fixed point decimals that the database system provides, because the CPU has instructions to operate on these very efficiently. Right? It's one instruction to take two floats and add them together or subtract them. But when we talk about dealing with the fixed point ones, that's a whole bunch of stuff we have to write, and that's going to be way more instructions. So this sounds like what we'd want to use, right? Because it's fast. The problem is, though, there's going to be rounding errors. Because the 754 standard, there's no way to exactly store decimals in hardware. So they have to approximate this. Right, so here's a really simple C program. I normally don't like to show code in class other than SQL, but this is simple enough that I think you should be able to comprehend it from your seat. So all we're going to do is we have two floats, x and y, and then we're going to print out the value of x plus y, and then we're just going to print out the constant 0.3. So you pick your favorite compiler. I use GCC, and when you compile it, you get this answer here. Right? That looks, that's correct, right? That's what we would expect. But all I'm doing is just doing %f. I'm just asking the languages to print out the floating point and let it do whatever rounding it wants to do. When you specify what precision you actually want, so I want to go 20 decimal points, then you see that you get a totally different number. Same exact code, same exact values. It's just when I represent it in a human readable form, now I'm seeing I'm way off. Right? I can't even get 0.3 correct. right? And this is because the hardware can't exactly represent floating point numbers to precisely, right? So again, this will be faster for us to execute, but we're going to have rounding errors. So now, you may think, all right, 0.3, my little example here, who cares if there's a rounding error? But if it's your bank account, then you start to care, right? Or if it's a scientific, instrument where you're trying to send something into space, these rounding errors cause real problems. So to avoid this, you use what are called fixed precision numbers, or fixed point decimal numbers. So again, these are something that database system has to implement to represent these values. It's a bunch of extra code that can take care of all the arithmetic operations or aggregations you normally wouldn't want to do on any kind of number, right? So the way, I'll show how Postgres is going to do this in a second, but the basic idea to think about this is you're going to store the value as like a varchar, the actual like human readable representation of the value, and then some extra metadata to say, here's what the decimal point is, here's what the scope is, here's the rounding information, right? And that's all packed in with the tuple itself, just as part of that byte array. So I always give this demo every year of Postgres and SQL Server. Right? I normally just give it for Postgres, but we'll try it for Oracle and SQL Server as well. So let's see what the performance difference is from these different types. Let me turn this off. All right, is that readable? All right. So what I've done is I've created I wrote a simple Python script, and all it did was create a giant CSV file that has 10 million rows of 2 floating point numbers, right? That's all it is, just random numbers. So I can load this. I'm going to create 2 tables in Postgres. I'm going to create one that uses reals and one that uses the fixed point decimals. Right? So there's one for reals. There's one for decimals. And then Postgres has a nice command called copy that will take a file that's on local disk and then take the output and write it into the table. Various database systems have various commands. In SQL Server, it's called bulk. In MySQL, it's called load into, whatever. Oracle was a pain to set up, but I got it working. So now what we're going to do is we're going to run a query that just takes the 2 numbers and adds them together. So let me turn on timing as well. And then because this is Postgres 10 added support for parallel queries. So like, take a single SQL query and split up across multiple CPUs and run them in parallel. So I'm going to turn that off as well, just so we see like the performance of a single CPU. And we'll do this for all the other systems as well. So let's see how long it would take if I do it with the reals. So if you've never seen this, let me go back to the syntax, sorry. So up here it says explain, analyze. So if you've never seen explain, what explain does, you put it in front of any SQL query, and instead of actually running the SQL query, it tells you what query plan it's going to use to execute the query. Right? It doesn't actually run. It says, here's what I'm going to do if I ran it. Different database systems have different syntax. This is what Postgres and MySQL do. Right? We'll explain what a query plan is. We'll explain what an optimizer is later in the semester. But basically what happens, just saying like, you want to run this query, here's how we're going to do it. So, but if I add the analyze clause in front of it, then this is actually going to give you the query plan and also run it for real. So you see that it basically took 1,200 milliseconds, so 1.2 seconds to run this. And this to show you if it's not a caching effect, I can just keep executing over and over again. And the performance, it got a little faster because it got in cache, but it should stabilize. Yeah, about 800 milliseconds, right? So let's do the same thing now for the decimal one. So 2.4 seconds. I run it again. It should get a little faster because it's in cache. Not much, right? So again, 2 same values, same data set, loaded as different data types, but the one query is twice as slow because we're doing all this extra stuff to deal with the rounding and other things, right? And you can see that, let me see if I try to run this again. Are they getting the same values? Right, they're getting different values here, right? Because there's some rounding issues. So we can try to cast this as a decimal. and then it'll be human readable. Right? So this is much different than this one here, right? This is 1, and this starts with a 9. So the real one is having rounding issues. So let's try the same thing in SQL Server. The data is already loaded, so we don't need to bother loading it again. So let me run this. So this will be with the reals. Produces a result. It told me it took 1.5 seconds. Just try it again to see whether it gets faster. Not much. And then I'll run the same thing now with on decimals, and it should be slower. Yeah, twice as slow. Run again, disapprove. Right? And this little max DOP, it's the degree of parallelism. It's basically telling SQL Server, again, run it with one thread. The last one I'm going to show is Oracle. And I had a breakthrough this weekend. I figured out how to get the up key to work. So it was not by default. All right, so it's already loaded. We'll do the same thing. Where is it, Oracle? So we'll turn timing on. Run it with the reals. And you get 0.53. Run it with decimals. The same. Slightly faster even. So what's happening here is that Oracle actually gives you the 6-point decimal no matter what. Even if you ask you want the real or the decimal, it always just gives you the decimal. Right? And before you say, oh, look how much faster Oracle is than the other ones, again, for this one here, like I didn't turn off multi-threading. But it also looks like it's rounding off a lot, right? This looks way off than what we'd expect from Postgres and SQL Server. And that's because Oracle has this thing where if the size of the output is not doesn't fit in whatever characters you specify with this num width thing, then it rounds it for you automatically. Took me a while to figure that one out, but here's actually what you get when you have the real number. So that looks like what we'd expect. So again, this is something that just be mindful that we have to implement this in our database system. This is not something that will magically go faster. It's not something we can rely on Harvard to provide for us. Yes.
Right. So does it do like rounding along the way, or does it only round at the end?
This question is it doing rounding along the way, or is it only at the end? As far as I know here, for this stupid num width thing, it's rounding on the client side. So the server is giving you this, and then it rounds when it lands on the client. Why? For whatever reason, I don't know. Right? And in Postgres and MySQL, so Postgres and SQL Server, like you can specify the round. There's a round function we could do on the server side. So I think we can do something like this, round. And then you say to what precision you want, so like 2. Nope. Different systems have different things. I think that's MySQL syntax. I don't know what Postgres. Anyway, so you can do in your application, you want to do it server side. You want the server to do it for you. You don't want to assume the client's going to be formatting whatever for you. Yes?
So it looks like in the Oracle one that the decimals is giving the same value as the reals in Postgres?
Let's see here. So his question is, it looks like Oracle is giving us the value of the real and not the floating point.
Something 153.
Yeah, hold up. So let's see. It was 3.
And then in Oracle. Oh, no.
That's Oracle.
Okay, never mind.
And
Why is the Oracle decimals not equal to the...
Let's try SQL Server. So we'll assume that's correct because it's SQL Server. So that was 9 something, and let's see what this gives us. 9 something, but it looks the same, right? Yeah, so that's different than what the reals gave us. I think reals was giving us like 7.7, and this is 7.5. So going back to Oracle. Oh, sorry, that's Postgres. Too many terminals. both the same. I don't want to decipher this live, but length 2. So maybe it's always a decimal. Sorry, it's always a real, not the fixed point. Okay, I'll double check that. Definitely declared it as a decimal. All right, let me figure out what's going on. I'll post on Piazza. Okay. Any other questions? All right, cool. So so what is Postgres actually doing? Postgres, SQL Server and Oracle are not open source. Postgres is, so we can actually look at it. So this is actually from the Postgres source code, version 9.6, I think. And so when you declare a fixed point decimal, this is what it stores. It stores this struct. So you have all this extra metadata about where the decimal is, what the sign is, and so forth. And then this part here, as I said, this is just a string representation of what the real value actually is. And then at runtime, they know how to take this and decipher it based on what these values are set to ensure that you have the correct computation. So now, why is it running twice as slow? So when you actually again look at the source code to say how is it actually doing addition, you see it's not just one instruction, number plus number. It's just giant switch table, a bunch of extra stuff to try to figure out if it's negative or non-negative, it's 0, or if they're equal to each other, right? So we're executing this for every single time we compute those, number plus number. Whereas if it's a floating point number, it's one instruction on the CPU. So, we don't have the source code for SQL Server and Oracle, but I guarantee you they're doing something similar, roughly. Okay, so is this clear? So if we don't want to lose data due to imprecision, we use a fixed point decimal. But this is something we have to implement in our database system for us. Okay. So now we want to talk about what happens when the value of the thing trying to store is too large and doesn't fit in a single page. So there's two ways to do this. So in general, as I said last time, the size of a page is going to be fixed throughout the entire table, or mostly throughout the entire database. There's something you set when you turn the system on. You say, I want to have 4 kilobyte pages or 8 kilobyte pages. DB2 allows you to play around with the page size per buffer pool, but in general, let's assume that's the case. So now what do we do if the thing we're trying to store doesn't fit in a single page, right? Well, an obvious thing to do is have what's called an overflow page. So basically in our tuple, say this attribute C here doesn't fit in the page, so we'll just have a pointer now to some other overflow page that'll have the data that we want. So this could just be another record ID, like a page number and an offset, to tell us where to find this particular data that we would need. So then, if we now have a query and we need this attribute or value as part of the output, we'd have to follow this pointer and go bring that page in, copy the data out, and produce it as an output. And now, if this data doesn't fit in this page by itself too, it can have another overflow page pointer to some other thing, some other page, and we just chain them all together to produce the output that we're looking for. So different database systems have different names for this. In Postgres, it's called Toast. In SQL Server and MySQL, they're called Overflow Pages. And they have different specifications of when they would actually use something like this. So in Postgres, if the value you're trying to store is larger than 2 kilobytes, then it always goes to this other thing. In SQL Server, it's just if the tuple doesn't fit in the page, it pulls it out and puts it into another page. And MySQL is half the page. So the reason why you'd want to do something like this is because you get all the protections you normally would get when these overflow pages with your regular data. Meaning, if I'm writing to this overflow page and I crash and come back, I don't want to lose anything, right? There's other optimizations you can do with these overflow pages that aren't easy to do in the regular slot of pages as well. Like in Postgres, for example, since most of the time these overflow pages are read-only, or read-mostly. Like, think of like on Wikipedia, you update an article or update an entry, but most of the time people are just reading it. So therefore, I could just compress this when I put out the disk or keep it in memory, and because most of the time I'm never going to have to decompress it to update it. So there's a bunch of optimizations like that, and they all come under the same protections as you normally would with regular data pages or regular tuple pages. Another alternative, instead of storing it directly inside the database, is to use what's called external storage. And the basic idea here is that we're not actually going to store the data for this particular attribute in the tuple itself. We're just going to store a pointer or a file path to somewhere on the local disk or network storage or some external storage device where this data can be found, right? So in this case here, going from C, this could just be a file path on the local disk to say, here's where to find this particular attribute if you ever need it, right? So in the systems that do support this, like Oracle and DB2 and Microsoft, you can't actually modify what's in this file, right? You can read it, but you can't manipulate it, right? Yes?
So the overflow pages reside in the memory, the place similar where tuples are there, and the external files are in the separated disk.
So his question is, or statement is, for the overflow page, this gets brought into memory just like a regular tuple page. Correct. In the case of these external files, where do these things reside? I mean, so if I run a query like select star on this tuple here and C's in this external file, if I need to produce it as an output, I gotta go read it in. So it could page it in just like another tuple or other tuple pages. It could be ephemeral, meaning like I'm gonna read it and then immediately discard it rather than polluting my cache. There's a bunch of different ways to do this. But the key thing to think about is like, if someone now outside the database system modifies this file, we'll see that change inside of our database system anytime we go to read it, because it's outside the control or the protections of our database system, right? So let me tell you guys, why do you want to do something like this? Or what's an example of a file maybe you don't want to store in the database system? Say you're building a website, right? And you have a bunch of video files. You want to, and you have a tuple that says, this person uploaded this video. You don't want to store the video in the database itself because that could be, gigabytes. Right? So it's very common to see that in those kind of things, right? The application frameworks like Django, Node.js, and things like that, they have built-in ways to store data outside the database system for images and other things. So there's no sort of set in stone rule to say how big a file should be, to put it out as an external file versus keeping it in an overflow page. I'll say also too, for the overflow pages, this is transparent to you as the application, so you don't know that you've gone to an overflow page, right? You can go do what we did before and look at the actual layout of and low-level information about where our data is actually stored, like we did with the CTID in Postgres and the other systems. But most applications don't care that it's stored in an overflow page. Like I wanted to get my data out. For this thing, again, depending on how it's actually implemented, you could go through the data system, or you could just jump to the file and go get it directly if you wanted to. So there was a paper written almost 10 years ago, over 10 years ago, by some famous database people at Microsoft. The name of the article is "To Blob or Not to Blob." A blob is a binary large object, right? It's a variable length binary data. And they basically found back in the 2000s that anything below 256 kilobytes you want to store as an overflow page. Anything larger than that you want to store in the in external file storage. We had the guy that invented SQLite come to CMU a few years ago, came and gave a talk here, and he said that for a lot of cell phone applications, it's actually better off to store the thumbnails from images, even up to 1 megabyte, inside the database system. Because that was much faster to read those records from the database system because they already had the file open, rather than having to follow this pointer to the file system and then do the fopen to go get the data. So again, there's no hard and fast rule of what to do. This is also more common when the database storage is super expensive, right? If you really care about your data or your database, you're usually going to run it on high-end hardware, and therefore storing like a bunch of video files in some really high-end enterprise disk is probably not a good use of your money. So you can take these files, chuck it in HDFS or cheaper storage like S3, and then now the data system is not overburdened with trying to maintain your files. So again, it's not just for performance reasons. There's other economic reasons why you want to do something like this. But this paper, I think, summarizes a bunch of the issues. That's why I like it. So again, any questions how we're going to represent data? Most of the times, for fixed length data, it's just whatever our programming environment gives us. For anything that's variable length, or if you want fixed point precision, that stuff we'll have to implement ourselves. Okay. So now let's talk about how we actually figure out what our tuples look like. So again, this is what the system catalogs are for. It's the metadata about the data, the metadata about the database. What columns I have, whether table names, what indexes I have, and so forth, as well as some other things like user permissions and security stuff, which I don't care about. And then this will come up later on when we talk about query optimization, but also internal statistics about what your data looks like. How many unique values do I have? What does the distribution of those values look like? So pretty much every single database system is going to store their catalog inside itself as just another table. So like eating your own dog food. So I'm going to store all the metadata about my tables in just tables themselves. All right? And so inside the source code, you obviously don't want to write SQL queries to say, what's the name of this table, because it's chicken before the egg problem. Like, how do I do a SQL query on a table to find out a table name if I need to know a table name, right? So you usually have like some C++ code or whatever your data system is programmed in to wrap around the low-level access methods to go access the catalog. All right. So most database systems will expose the catalog through the standard information schema API. So in the 1980s, all these different database systems all had their own way of saying, here's my catalog, here's how to access it. And that became a real pain in the ass now if you want to take your application and port it to from one database system to another, because now all the catalog stuff is different, and you got to rewrite all your code again. So in the ANSI standard, and I think also in the SQL standard by now, they specify this thing called the information schema that every data system has to support to say, here's the metadata about my tables. But we'll see in a second, they don't always expose the same information in these tables. And all the data systems are all going to have their own sort of shortcut ways to go get this information as well. So for example, say we want to get all the tables we have. So the SQL standard would say you write it with this, information schema.tables, which is just a view on top of the real catalog, and you give it the catalog name, right, or the database name. In Postgres, you use /d. In MySQL, you use show tables. SQLite is .tables. And then, again, all the data systems all have their own shortcuts. And essentially what they're doing underneath the covers is converting this command into something like this. Same thing now if I want to get the schema for a table. So again, this is how we do it in the ANSI standard. And then the various systems all have their own way of doing this. So I want to go a quick demo of Postgres and MySQL. Again, just to show you what's actually going on. All right, so again, Postgres, if I do -d, I get the list of all my tables. I can do -d plus and get more information. And then if I pick a table, it'll tell me what the metadata looks like. All right, so here's all the columns that I have. Here's the types I have. So then now when I run my query, I look at this information and say, all right, the first attribute is an integer. That's going to be 32 bits. The next attribute is also an integer. That's going to be 32 bits. And then I have code inside to say, all right, if I'm operating on this tuple, what is the schema? I know how to, again, do the conversion of the raw bytes of the byte array for that tuple and put it into the form that I would expect. All right? So let me see if I can do this for my SQL. I think I just destroyed my SQL. Let me do this on another machine. So I can say show tables. It tells me what tables I have. I can say show databases, same thing. And here's all the different databases I have. And then for a given table, I can say describe knobs, right? And it'll just say, again, same information. Here's the name of the field. Here's the type, and then some extra metadata. So this is MySQL 5.7. The newer version actually stores the tables in the catalog itself, or stores the catalog in the tables itself. In this version here, they didn't do that. all they would do for the catalog is just read the directory of where the database is stored and use that to figure out what databases are there and what tables are there. And so we can actually break it or fake it out by putting things that shouldn't be there in that directory. Right? So if you go back here, let me split it. So we do show databases. And it thinks I have a bunch of these here, right? So now if I go back to this machine, log in as root, go into where MySQL stores its data, lib MySQL, right? And roughly you see that there's a bunch of, there's a bunch of directories here for the databases that it knows about, right? There's a database called test, there's a directory called test. So what happens if I call now make directory xxx? Well, when I go back up here, MySQL thinks there's a directory called xxx. So this is a good example of where, if we rely on things external to the database system, we can't fully control that. So MySQL can't prevent anybody from going to that directory and putting whatever it wants in there. But it's relying on that to figure out what's in my database. So from an implementation standpoint, it might be easier. But from a correctness standpoint, it's problematic. They may say, who's going to be stupid enough to go create directories to screw around with MySQL? Well, what about other things like I'm writing the files that I don't have the regular protection I would for my regular data because I'm not logging things correctly, right? We want to put as much as possible inside the database system because then we can rely on that to perform correctly for us. Okay? All right. So that's it. That's all we really need to cover for catalogs this semester. Just be aware that there's something that inside the data system we're going to keep track of what our schema looks like, and that we're going to use that when we execute queries, use that when we build indexes to determine what should we actually be doing. And the way to think about this, the different types, is that in the most easiest way to implement this, and you'll see this in the bus type code that you guys work on, when you look at the type system, it's going to be a giant switch statement, right? If the type is integer, do this. If the type is a float, do that. And so you're doing that for every single tuple, and that's actually going to be really slow because you're essentially interpreting what the layout should be. And in the more advanced systems, you can actually compile or do code generation to compile on the fly, like just-in-time compilation in the JVM, to actually compile those operations so that you don't have to do that interpretation every single time. MySQL doesn't do that. New versions of Postgres does that. But Oracle and SQL Server should do that as well. All the major commercial systems do that. That's not something we're going to cover in this class, but when we cover query execution, I'll bring that up to say this is a way to actually make this run faster. All right. So the next thing we're going to talk about is for storage models. Is the first thing you have to realize that we covered in the first lecture is that the relational model doesn't say anything about how we actually want to store data. Doesn't know about types, doesn't know about byte arrays and so forth. And it doesn't necessarily even say that we have to store all the attributes of a tuple together, either in memory or on disk, right? And so again, anytime we so far in the class, when we visualize databases, I'm saying here's the row and here's all the attributes for it, right, for a tuple. But that may not be the best way to do it for some workloads. So let's look at a really simple database example here. Right, this is actually derived from the MediaWiki software that runs Wikipedia. Like if you go look at the source code, it's all PHP with MySQL. If you look at the DDL file, the SQL file, it'll look roughly like this. So we have three tables. We have user count, pages, and revisions. And so the revisions table is where we're going to store all the new updates for every single article. So it's a kind of a foreign key of reference to the user that made the change, and then a page ID that corresponds to the article or the page. Right, and this guy then also has a foreign key reference to say, here's the latest revision for this particular page. So you don't have to do a scan, you just can jump directly to it. Again, this is sort of an approximation or cleaned up version of what Wikipedia actually does. But for our purposes in this lecture here, it's fine. So there's two sort of general class of workloads we're going to care about in database systems. They're certainly not the only ones. There's machine learning and streaming stuff. But for now, let's just focus on just two. So the first is called Online Transaction Processing, or OLTP. Who here has ever heard that term before, OLTP? Few. Okay, good. So this is usually what you're going to end up with, this type of application, any single time you're building building a new application. Right? If I'm building a new website, I'm building a new iPhone app or whatever, you're typically building one of these. And so for transaction, OLTP or online transaction processing, the idea is that this is where we're getting new information. We're ingesting new data from the outside world and putting it into our database system. Right? So these queries can be really simple. They're only going to read a small amount of data or update a small amount of data. And we're going to be doing those same operations over and over again. So the example I always like to give is like the Amazon storefront, right? The website you go to when you buy stuff. That's considered an OLTP application because I'm adding stuff to my cart, I'm making purchases, I'm updating my account information. For each of those single operations, they're doing a lot of them because they have a lot of people buying stuff. But for you as one customer, you're not updating a lot of data. You're updating your account information. You're updating things to your shopping cart. So the queries that are running are only doing a small, accessing a small portion of the database. So the type of queries you would see, again, going back to the Wikipedia example. So here's go get the current revision for a given page. Here's to update my user account to say that when I logged in, and here's a simple insert query to insert a new revision. Right? Each of these things are accessing a small number of tuples at a time, but we're doing these things over and over again. So now the other type of workload is called OLAP, or online analytical processing. And this is when you've already collected a bunch of data from your OLTP application, and now you want to analyze it and extrapolate new information from it. Right? This is sometimes called, not I wouldn't say data science, but that realm of like taking a bunch of data you have and trying to derive new information from it.
Analytics.
What's that?
Analytics. Data analytics.
Yeah. I mean, it's in the name, online analytical processing. Business intelligence is another phrase for this. Decision support is another one. Big data, if you want to call it that, right? Again, in this workload, in this environment, we're not updating data, right? There's the OLTP side is getting that new information for us, and now we're trying to make sense of it. So a query might be on a Wikipedia example. Say we want to count the number of people that have logged in per month where their host name ended with .gov. Right? There was a scandal a few years ago where they found members of Congress were having their employees go to Wikipedia and scrub them clean to remove all whatever scandals the congressman was involved in. Right? So you want to figure out all the people that are logging in from sitting at the government doing this. So these types of queries are going to be read-only. They're going to read a lot of data. Like I'm going to scan the entire table, right? As opposed to OLTP where I'm updating one thing. I'm going to do a lot of joins, right? In OLTP, you usually don't see a lot of joins. So one way to grossly characterize these workloads is that on one end of one axis you say how complex are the queries? Are they really simple? Like if they're only accessing a single table, or are they doing complex joins? And then whether they're write heavy or read heavy. So OLTP would be down on this end of the spectrum. They're pretty simple queries, but they're doing a lot of writes. OLAP would be doing a lot of reads, but they're more complex. And then there's sort of this new class of workload called HTAP, or hybrid transaction analytical processing. That sort of is trying to do both of them, right? You still want to ingest new data, but you want to analyze it as it comes in. You see this a lot in anybody who wants to do decision making on the fly, as people are browsing websites. You see this a lot in like internet advertising companies. So now, given that we know about these different workloads, now we can talk about what is the right storage model to support these workloads more efficiently. So again, the relational model doesn't say anything about the layout, but we can be mindful of this when we decide how we want to build our data system. Yes?
So what is the relationship between OLAP and NoSQL or NoSQL database? MongoDB built for OLAP workloads or OLTP?
Okay, so this question is, what is the relation of OLAP to NoSQL or NewSQL systems? So I would say, does everyone know what NoSQL is? Who here doesn't know what NoSQL is? Few. Okay, that's fine. So, and most of you haven't heard of NoSQL or NewSQL. So these are workload types. And what you're describing, NoSQL versus NoSQL, those are sort of system categories. So the other question is, what is MongoDB for? What is the NoSQL good for? So the traditional NoSQL systems, MongoDB, Cassandra, Redis, they would be at this end of the spectrum. They're about ingesting new data, right? Mongo has some support to do some analytics, but when we talk about the column store stuff, they're not a column store. They're going to get crushed by any column store database. You wouldn't want to do hardcore analytics on MongoDB. You will support some queries to do this. MySQL and Postgres will support some queries that would fall under the OLAP category, but they're not going to be as efficient as running on a column store system. So NoSQL, basically, there was this movement in the late 2000s where all these companies are basically saying, look, Google is making a ton of money, and they put out this system called HBase, or sorry, not HBase, Bigtable, and this thing called Hadoop, and they're not doing SQL, they're not doing transactions, they're not doing joins, and that's how they're able to scale. So all these people end up building these NoSQL systems like Mongo and Cassandra that sort of fall under, try to follow those edicts or design patterns and to support, sort of modern, software 2.0 or web 2.0 applications. Right? But they would fall under this. Hadoop is OLAP, but like Bigtable, Cassandra, MongoDB, and those guys are over here. Then what happened is people realized, oh, well, I actually do want transactions. I do want SQL. I do want to do some joins. And that's where the new SQL movement came along. And this is what I was working on when I was in grad school. And actually, if you go read the Wikipedia article for NoSQL, it talks about my system was the first one of the first NoSQL systems. Right, and this is because I wrote the NoSQL article on Wikipedia, so I could say whatever I wanted. But the idea was they were trying to do, fast transaction processing and OLTP without giving up transactions or giving up joins the way the NoSQL guys did. Now, there's other NoSQL systems you could say, are like, again, there's a bunch of systems out there that don't do relational model that you want to do analytics on, but primarily most people think of these guys down here. I would say that the claim NoSQL, first they're like, oh, we're not going to do SQL. SQL's stupid. And then it came out, everybody but Mongo now supports some variant of SQL. So then they said, oh, NoSQL really means not only SQL. And some of them actually are starting to add transactions. Like MongoDB has support for like full-fledged distributed transactions. So all the things they claimed that were a bad idea, 10 years ago, turns out it is a good idea. SQL's not going to die anytime soon. People have tried to replace it, right? People have felt it was a bad idea in the 1970s, 80s, 90s, and 2000s. It always comes back, right? It's what people want. It's not the I like it because this is what I grew up with, but there's certainly ways to improve it, and some people have tried to do this. But the core idea of declarative language on top of your data is, I think, is one of the major contributions of Ted Codd's work in the 1970s. Okay? All right, that was a long soliloquy. Does that answer your question? Yeah. Okay. We can talk offline about if you want my opinion of other systems. Okay. So again, everything we talked about so far, when we show rows and tuples, or sorry, tuples, and this is why I don't want to use the term row, because when we talk about a column store, it doesn't make any sense. But every time I showed a tuple, I showed it as a row, right? And this is called the n-ary storage model. And so basically the idea here is that we're going to take all the attributes for a single tuple, and we're going to store them contiguously in our pages. Again, we can have the overflow pages for larger objects, but in general, it's all going to be aligned together, right? So this is going to be ideal for OLTP because, again, the amount of data we're going to access is going to be small in these OLTP queries, and it's going to be accessing for single entities. Go get my account information. Go get my orders, and I want all the data for that, for my account. I don't care about all the other, millions of customers. I just want my information. So for a Rowstore, that's actually really efficient because I just jump to the one page that has my data. I get it, and I'm done. All right, so let's see what this looks like. So again, using the Wikipedia example. So say this is a single page. So we have a header. Again, assume this is in the slotted page format. We have our header. And then we have the user ID, username, user pass, host name, and last login. And so When we only after we have the last attribute for our tuple, then we have all the other tuple data. Right? Everything is contiguous to each other. So again, now if I store this in my database, I can represent this in a single page. So now if I have a query that says, get all the account information for a given username and password, I can do a lookup and an index, which we'll cover in lecture 7. But that's basically going to tell me, hey, here's the page ID and slot number that has the tuple that you want. I do one seek, I do one read to fetch that page, bring it to memory, and I can jump to exactly to the location that has the data that I want. Right? So again, OLAP workloads are going to look a lot like this. Go getting the data for single entities or small number entities. So having all the data for a tuple contiguous to each other is the most efficient way to do this. Right? Same thing if I want to do an insert. My insert query is going to have all the data contiguous anyway. So I just find a free slot and just write it all at once. And now I can flush this out and this one disk write, ignoring the log. Yes?
So for what purposes is it useful to segregate that data into different pages?
So his question is, for what purpose would it be useful to segregate the data in 2 pages? Okay, so let's look at why this is the bad idea for some queries, and then we'll see why it's a good idea to segregate it. Right, when we talk about the decomposition storage model, the column store stuff. All right, so let's look at an example where the row store is a bad idea. So let's take that query I showed at the beginning where we want to get all the people from the government that are modifying Wikipedia pages when they shouldn't. So if we break down this query, right, we look at it, we realize we're actually going to need to touch all the data, right, because there's a full sequential scan across the user account table to find all the people that, look at all the user accounts and look at their host names. Right? Assume we don't have an index. For OLAP, you usually don't have indexes for these types of queries. All right, so now if I go read, say, the first page I read is this one. Again, we're in a row store here. So if I look at my query, I want to first do a where clause to look up the host name and try to match it with my pattern if it ends with .gov. So that means I basically just want these values here. So as I'm scanning along, I look at my catalog and says, well, I know I have for this table, I have 5 attributes, and you want the host name, so that's at this offset. So I go read what I want. And then I get to the end, and I'll jump to the next one, and so forth. The other part of my query is that I have this group by where I want to aggregate them together based on the login, because I want to get it per month, and then produce that as my final output. It's the count number of government employees that are logging in for each month. Now, so to satisfy this part of the query, I only need this column here, this attribute, just the last login field. So what's the problem?
You're reading 4 other columns.
What's that?
If you're reading 4 other columns, you have to read additional pages.
Exactly. So I have to read this entire page. Again, I can't, remember I said in non-volatile storage devices, it's a block-based API. So I can't just say, just get me exactly this data. I got to go bring in the entire page. So now you have all these columns here that I never even accessed at all in order to execute this query, but I had to bring it into memory from disk in order to get the 2 columns that I actually needed. So doing analytics on a row store is going to be painful if you have a lot of data, right? In my example here, I have 6 pages. Who cares? But if I have petabytes of data, and in this case here, 3 out of the 5 columns that I'm bringing in or attributes I'm bringing in is useless for the particular query, then that's a bad idea. That's an inefficient use of the hardware. So again, the n-area storage model, the row storage model, is going to be really fast for any inserts or updates or deletes when we're accessing the entire tuple. Right, we want all the attributes for a single tuple, and there's usually just a small number of tuples at a time. But if we have to do analytical queries in the OLAP workloads, we want to scan large portions of the table, then this is going to suck because we're going to bring a bunch of data in that we may not actually need for our query. So now it should be sort of obvious that this is where the column store stuff comes in, where instead of storing all the attributes for a single tuple together in a single page, we're actually going to store all the values for a single attribute across all tuples in a single page. Right, so again, this is where the column name is. We're just storing all the columns together contiguously. Sorry, all the values within a single column contiguously. So this is going to be fantastic for our OLAP workloads where we're read-only and we only want to read a subset of the attributes for a given table, right? So again, going back to our example here, so this is what it looks like as a row store. But so say now we just take every single column, and we're going to split that up. And now within a single page, we have just the data for that column. So here's all the host names together. And we have the same thing for user ID, last login, and the other attributes for this table here, right? So forth like that. So now I come back to this query we had before. So the first thing I need to do is do my where clause on host name. So now I just need to know, all I have to do is go bring in the host name page. Wrong color, but ignore that. I just bring the host name page in. I can then rip through that quickly and say, look at every single host name and do my predicate. Now I have a bunch of tuples that matched. So then I go back and bring in the last login page and just jump to the locations that I need within that and to get the last login information that I want to produce my answer. So say in a real simple case here that the last login data is one page, the host name is another page. So before I had to scan all the pages, and this one I only have to scan 2. Again, think of in extremes. If I'm talking about billions of pages, then that's a big difference. Yes?
Are you like storing the primary key with each of these columns?
So this question is, are we storing the primary key with each columns? Your real question is, how do I figure out, I have the host names that match, how do I then go look up in the last login column and figure out how they match? Next slide. Perfect. Any other questions? So there's a bunch of other stuff we can do with this that we're not going to cover in this class, but there's a bunch of other advantages you can get. And actually, if you come to the Vertica talk in 2 weeks, Vertica is super famous for this. So with the row store model, all the values within, or the attributes within the tuple, they're all roughly different domains, right? This is going to be a username. This is going to be host names. This is going to be last login, which is going to be like a timestamp, right? It's all sort of jumbled together. And so if I can then pack them all this data together that are the same column, now there's a bunch of compression techniques I can do because I know they're going to be all the same type, right? So let's say that I'm storing temperatures of the room, and it's 70 degrees now, maybe 70.1, 70.2. Like it's not going to fluctuate that much. Instead of storing the full temperature every single time, what if I just store a small delta of what the base temperature was when we first started taking measurements? And now I don't need to store the entire value all over again. I just store that smaller representation. I think of like if you run like gzip or snappy or whatever your favorite compression algorithm is, you can't compress an MP3 really well because it's already sort of compressed. But if it's a text file, then you can compress the hell out of that because there's going to be a bunch of characters repeating over and over again. So if you have repeated values in your attribute, then you can compress the hell out of it and get much better performance. So now when I want to go do a read, again, with every page fetch, instead of maybe getting 1,000 tuples, I could get like 10,000 tuples because it's in compressed form. And some systems actually can operate directly on compressed data without needing to uncompress it, which is a big win. Okay, we're not going to cover compression in this class. We spent a whole lecture in it in the advanced class, but I'm happy to talk more about it if you want. Okay, so now his question is, how do I figure out I had a match in one page, how do I find a match in another page? So in general, there's 2 approaches, but everyone pretty much does the first one. So the first choice is to have fixed length offsets. So what that means is that for every single value in a column, it's always going to be a fixed length. So again, think simple, like a 32-bit integer. So all these are going to be, each of these values will be 32 bits. So now if I have a match, say, in this column at offset 1, and I need to find the corresponding tuple in this column, I know that, say, this column is also 32 bits, and I can just do simple arithmetic and say, I want offset 1 times the size of each attribute, and then I know exactly where I need to jump to. Or translate that to the row ID, or the page number and slot number that has the data that I'm looking for. So this is probably the most standard approach. And of course, now the tricky thing is say, well, what if I have a bunch of strings that are very length field? Then you get into like, all right, can I compress it to a fixed length field, or can I just pad it out so it always fits in whatever the max size is? Different data systems do different things, but overall, this is the most common approach. The other approach, which there's like one system that does this, which I think is a bad idea. They might have gotten rid of it, but I forget who it is. Where you actually store for each value in the column, you store the primary key or an identifier for it. So then you say, all right, for the column 1, I'm looking at tuple 1. I don't want to get to tuple 1 in column B. I have another map or another way to do a lookup and say how to go find the offset location for that particular tuple in this column. Of course, obviously this has huge storage overhead because you're storing this for this extra 32-bit or 64-bit value or ID for every single value, which is wasteful. Right? All right, so the advantages of the column store is that we can reduce the amount of waste I/O for these OLAP queries because we're only reading the bare minimum amount of data we actually need. We're not bringing in things we're never going to need at all. We'll get better compression. We'll get better query processing, which we will cover in a few more lectures, because we know we're operating on columnar data. The downside is obviously that for anything that needs to access a single tuple, it becomes more expensive because now you essentially need to put together the tuple from the different columns back together, whereas in the Rowstore it's all just in one location for you. And then anytime you update or insert or delete, this becomes more expensive because you have to split it all up. So I would say that column stores are not a new idea. They go back to the 1970s. There was like this Swedish military division built this thing called Cantor, which essentially was, they didn't call it a database system because they used different language back in the 1970s. But if you go sort of read between the lines, at its essence, it is a column store database system. It was never released, never made public. It was only this internal project. But that's the first known implementation of a column store. The 1980s, there was a paper that described the decomposition storage model in more formal details to say, what's the storage format look like? What is the implications of having this storage model? Probably the most famous commercial implementation, one of the first commercial implementations, was this thing called Sybase IQ. It was an in-memory column store that Sybase released as an accelerator for their regular Rowstore database system. So it had to do extra work to keep the two in sync. It never really got big adoption because, again, it was sold as an add-on to their Rowstore database rather than its own standalone thing. But it was the 2000s when the column store stuff really took off. Vertica, again, was founded by Mike Stonebreaker, the guy who invented Postgres and Ingress. That was his company that got bought by HP. VectorWise is a in-memory version of MongoDB. MongoDB is out of Europe. It's an academic project that's still around today. Right, so these are sort of the first sort of column store systems that were made in 2000s. But then it quickly became obvious that this is the right way to build database systems for analytics. So pretty much everyone now has their own column store system. And actually, I wanted to give a demo of Vertica today. I couldn't get it running. I did get the MariaDB column store working. And it's definitely a column store, but it doesn't mean it's actually good. So there's a bunch of stuff we'll cover as we go along for query optimization and query execution. Just because you're a column store doesn't mean you're magically going to go faster. I was actually able to get Postgres to beat the column store for analytical queries because of how you execute the queries, how you actually look at the data, and what the query plan looks like. So there's a bunch of extra stuff we have to do that we'll cover for the rest of the semester that you want to do if you're a column store that not everyone does. Okay? So any questions about column stores? So if you go off and graduate from CMU and you want to do analytics and someone's like, let's do it on Postgres, but it's a Rowstore, don't do that. Right? There's enough column store systems that are out there that you want to look at. They're not cheap though, at least for the commercial ones, but there's some decent open source ones. Okay? All right, cool. So the main takeaways from this is that, as we showed, the underlying representation of the storage of the database is not something we can just sort of put in our storage manager and not expose to any other part of the system. As we go out the rest of the semester, you'll see that a lot of times I'll say, like, all right, this is the way to do it if you're a Rowstore, this is the way to do it if you're a column store. And that's because, again, if we know the data system knows more about what it's actually doing, what the data looks like, it's going to make better decisions, better design choices, and in order to get more efficient execution. The other thing to also remember too is basically for OLTP, you want to use a Rowstore. For OLAP, you want to use a column store. Right? This simple rule will carry you out the rest of your life and make your life easier. All right, so now the last two classes we covered this problem here, how to actually represent the data in the database. So now, starting on Wednesday, we'll talk about how do we actually bring the data in and bring it to memory and manage that. Yes?
Is there any good reason to do a mix of the two?
This question is there any good reason to do a mix of the two? So we actually built our data system that did a mix of the two. We threw that away and started over because it was a bad idea. It was too much engineering overhead. There are some database systems will give you both. They'll expose so MemSQL, for example, you can say, create this table and it's a row store. Create this other table and it's a column store. And they have essentially two separate storage managers, two separate execution engines to operate on them. So those are sort of called hybrid storage systems, hybrid data systems. We were all in. I thought that was a good idea. I think it's a bad idea now. For in-memory, we think we can do fast enough transactions on a column store. For disk, it's a little bit more complicated. So there are systems that do both. They didn't really take off as much. So usually you see things like you could have a single interface where they have, you write one query and then underneath the covers, it figures out where you want to go to the row store or the column store side. There's ways to do that, but having a single software architecture that can manage both, I think is rough.
Why don't we store 2 copies of the same data?
He says, why don't we store 2 copies of the same data? Great, think of it extremes. My database is 1 petabyte.
Okay, but
So
lower data.
I don't have slides ready, but that I could easily find. But I can cover this next class. But basically, what people do is you have your front-end OLTP systems, and that's running MySQL or Mongo, whatever you want, and then you stream the data out over time to a back-end data warehouse. And then you basically can prune out the latest data on or old data on the OLTP side when you don't need it anymore. So you see this in eBay. eBay only retains the last 90 days of auctions. And after that, they prune it out. And that's because they want to keep the OLTP side nice and trim and fast, but then they still retain everything else in the back-end data warehouse where they do all the analytics to figure out what people are buying and what they're doing. That's the standard setup everyone does, right? And whether or not that's MySQL plus Vertica, like 2 separate database installations, or whether it's a single hybrid database, like Splice Machine can do this, or MemSQL could do this. Depends on what you want, how much money you have and what you're willing to do. I think that what we found for our own system is that building, having a sort of single storage manager try to manage both of these things was a bad idea, among other things. Okay, someone brought up testing last time, and I really want to spend time talking about that, but we don't have any time today. But again, next class, we'll start talking about the buffer pool, and hopefully we can talk about testing a little bit at the end, okay? Any other questions? Hit it.
Oh yeah, coming through with my Shaolin crew. 2 cents for a case, give me St. Nas brew. In the midst of broken bottles and crushed up cans, met the gals in the jam, oh I'll try. It's with St. Nas in my system. Crack another, I'm blessed. Let's go get the next one and get over. The object is to stay sober. Lay on the sofa. Better yet, down my shoulder. I'll be Tim, stretched out. Could never be son. Ricochet jelly, hit the deli for a cold one. Naturally blessed, yes. My rap is like a laser beam. The bullets in the bushes. St. Nas spin like canteen.
Crack the bottle up and St. Nas. Sipping through those who don't realize the drinking ain't only to be drunk. You can't drive, keep my people alive. And if the thing don't know you from a can of pain.